Hi, welcome to the AWS Quick Learn series. I'm Tej Arora, an AWS CSAA. In this video, I'm going to cover EC2. EC2 is the Elastic Compute Cloud Service. What it does is it provides on-demand and dynamic procurement and release of compute capacity. And what that means is procurement and release of VMs and dedicated hosts on which you can run your applications. And note that the turnaround of procurement and release is in minutes and it's not in hours or days like it used to be in the traditional data centers. Now, EC2 is the sort of the brains of Amazon Web Services. Everything you run, any application you run in the cloud, in the AWS cloud, runs on EC2 directly or indirectly. It is one of the oldest services, been around since August 2006. And given all the years of improvements and innovations by AWS, it is an extremely sophisticated service. So one of the characteristics of EC2 is that it's highly available compute capacity. It has 7 times fewer downtime hours than the competition, and it provides a 4 nines monthly uptime SLA. The service is available globally in 24 regions. It provides a huge variety of instance types for all different kinds of your workloads and applications. It provides amazing flexibility to tailor the capacity to your requirements. And it also helps you optimize your costs by providing almost 300 different instance types that you can tailor to your requirements. So you get different processor types in AWS EC2, Intel, AMD, NVIDIA, and so on. You get different kinds of memory and storage, such as SSD storage, NVMe storage, or magnetic drives. You can get host local storage or remote storage. There's a host of networking options with bandwidth all the way up to 100 gigabits per second using enhanced network interfaces. You get your choice of operating systems, and there's a variety of purchase models: on-demand, reserved, spot, savings plan. In terms of use cases, everything you run, every application workload that runs on the AWS cloud uses EC2 either directly, where you procure your VMs or hosts, or indirectly. For example, when you use RDS, behind the scenes, these instances run on EC2. Let's look at some of the key resources and concepts. AMI is an Amazon machine image. It's essentially a template that's prepackaged and it's used to launch an instance. What does an AMI contain? It has the operating system, application libraries, applications, configuration files, and so on. The storage volumes to attach to the instance, the network interfaces that are part of the instance are all defined by an AMI. A specific AMI may not support all the different 300 instance types. The sources of AMIs include you can create your own. There are shared AMIs available. There's community AMIs, and there's also AMIs you can purchase on the AWS marketplace. There's 2 kinds of AMIs: EBS-backed AMIs and an instance-backed AMI. Let's take a look at the differences between the two. So in this column, we have the EBS-backed AMI, and here the instance store-backed AMI. Now, instance store, remember, is host local store. So it's storage from the physical host on which your virtual machine is running. The EBS-backed AMI boots very quickly in about a minute. The other AMI takes about 5 minutes. And the reason for this is that all the contents of the AMI have to be retrieved from S3 in order to boot. Whereas for an EBS-backed AMI, just the information needed to create the boot volume is required at first. The rest can come later. The size limit for the root volume is 16 terabytes versus 10 gigabytes. The root device volume is an EBS volume. I've covered EBS in another Quick Learn series video. And in this case, the root device volume is an instance store volume. In terms of persistence is where there's major differences. The root volume by default is deleted when the instance terminates. Data on any other volume persists by default. But you can change these when you launch an instance. The data on instance store volumes persists only during the lifetime of the instance. So if you stop your instance, it's as good as losing all this data. This data is not persisted. For an EBS-backed AMI instance, you can change the instance type, the kernel, RAM, and user data. We'll talk about user data later. You can change all this while the instance is stopped, and then you can restart the instance. For this, all these attributes are fixed for the life of the instance. For EBS AMIs, you're charged for instance usage time, the EBS volume store, and your storing of the AMI as an EBS snapshot. Here you're charged for instance usage and storing your AMI in Amazon S3. The creation of an AMI that is EBS backed can be done with a single command, whereas an instance store backed AMI takes a little more effort. As I mentioned, an EBS backed AMI instance can be stopped, and when it's stopped and not running, the root volume is persisted in Amazon EBS. Instances based on instance store backed AMIs cannot be in stopped state. They are either running or terminated. An AMI is associated with launch permissions. These are permissions granted by the owner of the AMI. So it can either be public, which means the owner has granted launch permissions to all accounts. Any account can use the AMI to launch instances. Permissions can be explicit, in which case the owner grants the launch permissions to specific accounts, and launch permissions implicit means the owner has implicit permissions. Now, what is an instance family? It's classifying an EC2 instance into one of these 5 broad families. So let's take a look at these families. General purpose, compute optimized, memory optimized, accelerated computing, and storage optimized. And these have been set up to cater to different kinds of workloads. So a general purpose family is good for a variety of diverse workloads. The compute, storage, memory, and network capacity is kind of balanced. No one attribute dominates. This is good, for example, for running web servers. A compute optimized family consists of instances with a very high amount of compute capacity, CPU capacity, and this is good for workloads requiring high performance computing, such as weather prediction and media rendering. Memory optimized family has instances with large amounts of memory, and this is great for workloads needing tons of memory, such as in-memory databases. Accelerated computing is instances with additional coprocessors or hardware accelerators. So workloads needing these special processors can use this family of instances. So examples of special coprocessors include GPU processors for graphics or machine learning applications, or FPGA hardware, which stands for Field Programmable Gate Array, for scientific computing. And finally, the storage optimized family has tons of storage, and there's 2 sub cases. So the first is where there's a large amount of sequential I/O capability on a large amount of cheap storage. So workloads needing sequential I/O and a lot of storage that is cheap can use this. And what this provides is best price per gigabyte of storage and the best price per unit of disk throughput. So the characteristics are high GB of storage and high disk throughput. This uses a local instance store hard drive, and there is no built-in redundancy. You can get up to 3.5 gigabytes per second read throughput and 3.1 gigabytes per second write throughput. This is good for running Hadoop clusters and distributed file systems. And given that there is no built-in redundancy, the application on top has to have its own redundancy. The other kind of storage in this family is very low latency random I/O storage. So what this provides is the best price per I/O operations per second. It uses storage local to the instance, that is of NVMe SSD kind. And just like the HDD local store, it There is no built-in redundancy, and it can provide up to 3.3 million random read operations per second and 1.3 million random write operations per second. And the throughput, as you can see, is also pretty high, 16 gigabytes per second read and 8 gigabytes per second write, compared with sequential IO storage, where the throughput is much lower. And this storage is ideal for databases such as NoSQL databases or OLTP databases. Now let's look at instance type. Each of the families that we just discussed, it has multiple categories. So for example, the general purpose family has categories A, T, M. Compute has C. Memory optimized has RxZ, high memory. Accelerated computing family has the categories P, G, F, and INF, and the storage optimized family has the categories I, D. Now within each category you have revisions. So the T category will have T1, T2, T3, etc. Now an instance type is identified by a name. For example, T2.micro, T3A.extra large. This name is formed by a category within a family plus the revision level and the size. Now, what are the variations between instance types? What varies is the number of CPU cores, the amount of memory, the amount of storage, and the network bandwidth. Type of CPU, the network bandwidth between the EC2 instance and EBS, whether there is a CPU burst capability, we'll talk more about this in a moment, and the different types of storage that's available. So here's a quick look at the 5 families, and within each family you have these types, the A1, T3, T3A, and so on. And you can see for different families, there's different attributes of the EC2 instance that's highlighted. For example, for accelerated computing, there is an attribute of the number of inferentia chips. For the storage optimized family, you can see the attribute of local storage, which is a highlight of this family. Now, given this vast array of different kinds of instance types, how are you supposed to choose the right type for your workload? So first thing you do is you broadly map your workload to one of the families. Is there a dominant resource that your workload uses, such as compute or memory or storage? And then within your family, you can further refine and look at the different categories and map your workload. Remember that the AMI has certain memory requirements. And then once you've done a broad mapping of your workload to a type, you can better understand your application profile through load testing. And this is important so that you don't have any surprises in production of being heavily underutilized or overutilized instance type. And additionally, at runtime in production, you can monitor CloudWatch metrics for CPU utilization, disk utilization, network utilization, and so on, and further refine the instance type that is right for your work. Now, let's look at an instance lifecycle. An instance is launched, it can be stopped and started, it can be hibernated, and it can be terminated. In order to launch an instance, you need to specify a huge number of parameters. These are most of them. So you need to choose the AMI, an instance type, you need to choose a VPC, a subnet to launch the instance into, and whether to assign a public IP or not. You can choose a placement group and whether to use a capacity reservation. I'll discuss that more in a few minutes. Whether to assign an IAM role to the instance, and this IAM role assigned is also known as instance profile. It is essentially assigning the EC2 instance a role which is associated with certain permissions to access other services when the instance is running. You can choose shutdown behavior. You can choose to have termination protection, which means this instance cannot be terminated until this flag is changed. You can choose the type of tenancy. You can choose EFS file systems to mount, the scripts to run on startup of an instance. You can attach a whole bunch of storage volumes and choose encryption options for these volumes. You can associate a bunch of tags and security groups for the instance. I've discussed security groups in detail in the VPC Quick Learn video. Essentially, they're like a software firewall for your instance. Now, why would you want to stop and then start an instance? So if your instance is not in use and you want to stop the billing hours for your instance, that's a good time to stop it. Or if you want to resize an instance or change the instance type, that's another time when you can stop an instance. Hibernate is very similar to stop. So it stops billing. If you want to stop billing when the instance is not in use, you can hibernate. Remember that the hibernate feature must be enabled during instance launch. And what hibernate gives you that stop doesn't is that it also saves the RAM of the instance to an EBS volume, to the EBS root volume. So since the RAM is saved, the startup of the instance is faster and you get back the original runtime state of the instance when you stopped it. Now, if the EBS root volume is unable to hold the contents of the RAM, hibernation fails and the instance is just stopped. For hibernation to work, the EBS root volume must be encrypted. And compared to stop, when you hibernate an instance, there are additional charges because the RAM storage is being saved to the EBS root volume. So that extra storage used translates to EBS storage charge. Termination is when you no longer need the instance or you want to replace it with something else, you can just delete it. And all charges stop when you terminate. The charges for the instance stop and any volumes that are deleted on terminations also stop incurring charges. Let's take a quick look at the lifecycle states. So an instance, when it's launched, it goes to pending state before going to running state. And when it's in running state, it can be rebooted, terminated, stopped and started, or hibernated. When rebooted, it goes to rebooting state before it goes back to running. When terminated, it goes to shutting down state before going to terminated state. When stopped or hibernated, it goes to stopping state before going to stopped state. It's important to note what happens to the properties of the instance when you reboot, terminate, stop, start, or hibernate. So when you reboot, the instance remains on the same host. Its private and public IPs remain the same. The elastic IP stays associated with the instance. The data on instance store volumes is preserved. The root device volume is preserved. The RAM is erased. And there is no impact on billing. When you shut down an instance, the instance is deleted, its private and public IPs are released, the elastic IP becomes disassociated, the instance store volume data is erased, the root device volume is deleted, the RAM is erased, and the billing stops. Now note that stopping and hibernating is only possible with EBS-backed instances, which means instances that use the EBS-backed AMIs. When you start after stopping and hibernating, the instance may move to a different host. The private IP remains the same in both cases. There is a new public IP assigned to the instance by AWS. The elastic IP that was associated stays associated. The data on instance store volumes, this is other than the root volume, any instance store volume that is attached, the data is erased. The root device volume, which is necessarily an EBS-based root device volume, that's preserved. The RAM is erased in the case of simple stop and start, but for the case of hibernate, the RAM is saved to a file on the EBS root volume and it's used to restore the RAM when the instance is started. Billing stops in both cases and resumes when the instance goes back to running state. Now, an instance health check. There's two kinds of health checks. There's an EC2 health check and an ELB health check. ELB is the Elastic Load Balancer health check. So an EC2 health check, you can use it along with EC2 Auto Scaling to replace unhealthy instances. An ELB health check is used by the load balancer to stop routing to unhealthy instances and keep routing to healthy instances. EC2 Auto Scaling can also use an ELB health check to replace unhealthy instances. In other words, you can use the ELB health check or the EC2 health check with auto scaling. Launch configuration, launch template, and auto scaling group. I'll be discussing all of these under auto scaling in a few minutes. A placement group gives you control on where a launched instance is placed. Normally, the EC2 service would place instances across underlying hardware, that is across different racks of hardware, so as to minimize the impact of failures. But you can change that by specifying a placement group. So there are 3 different types of placement groups you can choose. If you choose the cluster placement group, instances are placed close together within one availability zone, and the key thing is that the inter-instance network bandwidth is very high. So normally you can get 5 gigabits per second between EC2 instances, but in a cluster you get 10 gigabits per second between EC2 instances, and this is for a single connection. A cluster placement is good for high performance computing applications that need very quick, low latency and high bandwidth node to node communication in the cluster. So in the cluster placement group, you cannot mix different instance types, and the types that are suited to the cluster placement group include cluster compute instances, cluster GPU instances, and high memory cluster. The next type of a placement group is partition. So instances in this group are spread across partitions, and no 2 partitions share underlying racks. So you may have a partition 1 with 3 instances on one rack and a partition 2 with 4 instances on a different rack. Unlike cluster, partitions can span availability zone, but they have to be within a region. And a placement group is ideal for distributed workloads that replicate for redundancy. A spread placement group, like the name implies, no instance shares underlying hardware. It's good for use cases where you have a small number of critical instances and they should not be failing together. So they need to be on, each instance needs to be on an independent rack. And like partition, spread group instances, they can span availability zones, but the limitation is that you can have a maximum of 7 instances in a spread placement group. Now, what are the constraints associated with using placement groups? An instance cannot be in 2 different placement groups, and you cannot take 2 different placement groups and merge their instances into a new placement group. Now, instance security, there's 2 aspects to it. Security groups are like a software firewall. In terms of logging into an instance, there's 2 ways to do that. You can do an SSH login to the DNS name for an EC2 instance using what's called a key pair. It's a PKI based public private key pair. This key pair is generated by EC2, and the public key is copied to the instance at launch time, and the private key is downloaded by the user, and this private key is used to do the SSH login. Another way to log into instances is the EC2 Instance Connect feature. And the big advantage of this is that there is no need to manage key pairs in EC2 like in the previous case. So public keys are dynamically generated and pushed to instance metadata whenever a login is required. And the SSH daemon on those instances, they use the keys from the metadata. And these keys live for 60 seconds. You can set up permissions in IAM for specific users to be able to use the Instance Connect feature to connect to an instance. And you can connect from a browser. You can use the AWS CLI to connect, or any SSH client to connect to EC2 using this Instance Connect feature. In addition, Instance Connect requests are logged to CrowdTrail, and this helps you get an audit trail of all the instance logins, which you do not get with plain SSH login. So when you use Instance Connect, you need to have Instance Connect installed on the EC2 instance. You need to go ahead and configure IAM permissions, without which it cannot be used by users. And when you use an SSH client, you need to generate a key pair and then run an Instance Connect command to push the public key to the instance. Let's look at storage options. So you have EBS volumes, which provides block storage. You also have instance store volumes, which provide block storage. You have access to S3 object storage, and you can leverage file storage using the EFS service. So the EBS volumes, you have the HDD and the SSD options. You can have EBS volumes optionally encrypted at rest using the KMS keys. And with EBS volumes, you have the option of using EBS optimized instances, which means the network bandwidth between EC2 and EBS is not shared by other network traffic, so it's dedicated. Now, instance store volumes have the HDD, SSD, and NVMe SSD options. Note that the NVMe SSD is encrypted by default using the hypervisor key, which is unique for every device instance, and you cannot use KMS for key management. The HDD and SSD options are not encrypted. Only the NVMe SSD storage is encrypted. So when you use HDD or SSD, you can implement your own file system level encryption. S3 I've covered in detail in another quick learn video. The EFS service, which is a file system service, allows you to mount these file systems on Linux-based AMIs using this NFS v4.1 protocol. Note that an EFS file system can also be mounted on-premises machines, which enables data sharing between on-premise and AWS cloud. Networking options. I've covered a lot of this in the quick learn video on VPC, but I'll do a quick summary here. When an instance is launched, a primary private IP is assigned to the ETH0 network interface. This primary private IP has to be from the subnet CIDR range. A customer can specify it, but if not, AWS assigns it. Again, it has to be from this range. And this primary private IP is associated with an internal DNS hostname. You can also have additional secondary private IPs, but again, they must be from the subnet CIDR range, and these secondary private IPs can be associated with any of the network interfaces. Now, if a subnet is configured to assign a public IP to an instance in it, and you have not disabled the public IP assignment during instance launch, then you get a public IP assigned to the instance. This public IP is from an AWS pool, and the customer cannot choose a specific IP. AWS associates an external DNS hostname with a public IP. Please keep in mind that when you stop and start an instance, the public IP can change. When you resolve an external hostname inside a VPC, it resolves to a private IP address. Outside the VPC, it resolves to the public IP address. In addition, there is an elastic IP. It's something that it's a public IP and it can be acquired and released by a customer and then associated with an instance or disassociated from an instance. And unlike a public IP, an elastic IP remains with an instance when you stop and start. Also note that once you assign an elastic IP to an instance, any public IP associated with it is released back to the pool. Now let's look at some limits associated with networking between EC2 instances and other components. So between instances within a region, you can get up to 5 gigabits per second per connection. It's 10 Gbps for instances in a cluster placement. And across different connections, it can be as much as 100 gigabits per second in each direction. Between an instance and S3, you can utilize the complete bandwidth available to the instance. And between an EC2 instance and the internet, it's up to 5 gigabits per second in each direction. Now, enhanced networking is a feature that enables very low latency and high throughput network connectivity compared to a regular TCP. And the reason this is possible is because the virtualization of the network hardware uses a special technique, SRIOV, which stands for Single Root IO Virtualization, that provides higher IO and consumes less CPU. The enhanced networking is useful for HPC, high performance computing apps, highly parallel applications that use message passing. So there's low latency, high bandwidth communication between nodes in this cluster. There is no extra fee for using enhanced networking. However, the instance types that support enhanced networking have a built-in cost for this, which is higher compared to other instances. without enhanced networking. It is supported only on VPC instances and not on classic instances. Let's look at enhanced networking interfaces. There's three kinds. There's the Intel 82599 virtual function that provides up to 10 gigabits per second. The Elastic Network Adapter or ENA that provides up to 100 gigabits per second, and Elastic Fabric Adapter or EFA, which is very similar to an ENA, but it has one additional feature that gives it more performance, which is that it bypasses the OS kernel. However, EFA is limited to traffic in a single subnet, and the EFA interface cannot be attached to a running EC2 instance. It must be attached either when it's stopped or at launch. And you can only have one EFA interface per instance. Now let's look at elastic load balancing. I will have another quick learn video on this, but just a quick summary. It routes traffic, request traffic to EC2 instances. And what's an EC2 compute unit? Given that there are 300 different types of instances, it's very difficult to compare the instances without a normalized measure of compute capacity. So EC2 compute unit is a measure of processing power that an instance provides. It's a standardized measure, so it's easy to compare different instances and their power. Now let's look at the features that the EC2 service provides. Auto scaling is one of the most important and key features used by sophisticated workloads. There's two kinds of auto scaling: EC2 auto scaling and AWS auto scaling. Let's look at EC2 auto scaling first. It is a managed service that helps you automatically launch or terminate EC2 instances in order to maintain an optimal capacity of your instance fleet. So you can use auto scaling for fleet management. And what this term means is that you pretty much detect and replace unhealthy instances. So you maintain a certain size of your EC2 instance group. Or you use auto scaling for dynamic scaling. And what that means is you add instances when your usage grows, or you remove instances when the usage drops. And you can use auto scaling for a combination of both as well. Note that addition or removal of instances, it happens within minutes. And if the elastic load balancer is used, it is integrated with EC2 auto scaling, which means ELB removes old instance and adds new one automatically. If you do not use the elastic load balancer, then how are requests routed to instances that are added and not routed to instances that are removed? Well, there's two options. You can integrate with Route 53 routing capabilities, or you can use your own reverse proxy, which performs functions similar to AWS elastic load balancers. So we know what EC2 auto scaling is used for. Now, the auto scaling group is a key construct. Essentially, it's a logical resource and it represents your fleet that you want to auto scale. For example, it could be a web server fleet or it could be an application server fleet. The elastic load balancer can be associated with an ASG and it routes requests to instances within the ASG. And as the ASG size evolves, the ELB automatically takes care of routing requests. Note that as long as the ASG resource is around, all the instances in it are around. So if you delete an ASG, all the instances in the ASG also are terminated. And when you create an ASG, instances that are specified in the auto scaling group are launched. When auto scaling actions happen, SNS notifications are sent and you can subscribe to them. So when a new instance needs to be launched, how does ASG know what configuration to use? You may recall that there's a lot of different parameters to specify when launching an instance. So there are two mechanisms. One is a launch configuration that you need to create. It's the old way, but it still works. Or you can create a launch template. This is the new and the recommended way. So a launch configuration, essentially it's a template with all the configuration needed to launch an instance that you would have specified when you launched an instance, let's say from the EC2 console. The launch configuration must be created before an auto scaling group is created. And a launch configuration can also be created directly from an existing EC2 instance. Now you can have one launch configuration per auto scaling group, but the same launch configuration can be used by many auto-scaling groups. And note that once you create it, you cannot change it. You have to create a new one and associate it with an auto-scaling group if you want to make any changes. The launch template, very similar to a launch configuration, but you can use a launch template not just in an auto-scaling group or not just from an auto-scaling group, but you can also use it from the EC2 console. You can use it from CLI or SDK as well. And in addition, launch templates have versions, so you can better manage different templates as they evolve. Note that an auto-scaling group is regional. All the instances are within a region. An auto-scaling group can include instances of many different kinds. So you can have different instance types. They can be in different availability zones, and they can be using different purchase options. So I may have some instances using the reserved instance purchase option, some from the spot purchase option, and some on-demand purchase option. We'll get to discussing these soon. Normally, an auto-scaling group, it automatically launches instances across availability zones and tries to balance the instance counts across the availability zones. Now, in terms of purchasing options, you can specify the split across different purchasing options when you create the auto-scaling group. Now, for an auto-scaling group, the size of the instance pool can be configured with these parameters. So you can specify a minimum number of instances, maximum, and a desired goal in terms of capacity. Now let us look at the scaling techniques that you can use with EC2 auto scaling. So one strategy is that you can maintain the same number of instances at all times. Essentially, if an instance fails, detect that and replace it with a healthy instance. You can also scale manually, so you can adjust the min, max, and desired capacity parameters, and the instances are automatically added or removed. Or you can attach a running instance to an auto scaling group or detach from an auto scale. You can also schedule scaling actions, so specify a date and time when actions are applied. This is good for computing that is predictable on a cyclical basis. For example, running a report between midnight and 2 a.m. To run the report, you need extra capacity, and you can schedule scaling at that. This is the most common form of scaling, which is policy based and dynamic. So you specify policies, and the policies track CloudWatch metrics for the EC2 instances in your scaling group. And when the metric reaches the alarm state, a scaling action is taken. Note that the metric is an aggregate value of all the instances in the auto scaling. So dynamic scaling approach is a reactive approach in response to changes. You can have multiple policies in an auto scaling group, and these are the different policy types that you can specify. So one policy is target tracking. You choose a target metric, choose a value for it, and the auto scaling group automatically maintains that target value. So for example, if you want to maintain CPU utilization at 65% or the SQS queue length per instance to be a certain number, the instances are automatically scaled up and down to try and maintain this target. This is the policy that is most commonly used, and it suffices in most cases. The step scaling policies, using that you can specify several thresholds for a metric, and at each threshold how much to scale. With the simple scaling policies, you specify a low and a high for a CloudWatch metrics, which is essentially just two thresholds, and you can specify how much to scale at these two thresholds. Now, besides these, you can also have predictive scaling. For that, you need to use AWS Auto Scaling, which we'll discuss in a moment, along with EC2 Auto Scale. This is a proactive approach as compared to the policy-based reactive approach to scale. Lifecycle hooks are actions you can configure for when a new instance is added or an instance is terminated as a result of auto scaling. These hooks can be used to prepare an instance with things such as installing software and configuring software. It can also be used to copy data from an instance that is being terminated. You can specify Lambda functions in these lifecycle hooks. So when there is an instance launch or a termination as a result of auto scaling action, a Lambda function is invoked which does whatever you need. Now, when scaling in, how does AWS choose which instance to remove? One way you can control that is by specifying a termination policy, or if you have certain instances that you do not want terminated, you can set the instance protection flag for those instances when you launch them. Now that we've seen EC2 Auto Scaling, let's take a quick look at AWS Auto Scaling. What AWS Auto Scaling does is help you scale multiple resources across multiple services. And the services that can be managed together from AWS Auto Scaling are EC2, DynamoDB, Aurora, ECS, etc. Note that a cloud formation stack is the basis for specifying auto scaling parameters. So you can have multiple EC2 auto scaling groups that can be managed from a single place. And a scaling strategy per resource type, such as EC2 auto scaling groups or DynamoDB tables and so on. There's these 4 different strategies, scaling strategies that you can configure. You can optimize for availability, which means there is a low utilization target, which is a threshold to decide whether to add or remove instances. You can balance availability and cost, in which case the utilization target is medium, or you can optimize for cost, in which case the utilization target is high, or you can have a custom where you can set the target yourself. A very important feature is instance resizing. Like I mentioned before, if after launching your application, due to the load on your system, if you determine that the instance is under or overutilized, you have the ability to change it. Also, when new generation instance types are launched, you can move to them if you wish. For an EBS backed instance, you just need to stop it, you change the instance type, and you start. And that's all there is to it. With the restriction that the new type that you specify, it must be compatible, in terms of the virtualization technology used, the architecture, the NVMe support, the AMI used, and whether enhanced networking is used. So they have to be compatible on these aspects. For an instance, store-backed instance, you cannot stop and change and start. You just have to migrate your application to a new instance. Instance recovery is an option. So you can set up CloudWatch alarms to monitor instances that have had a hardware failure or a failure which AWS needs to fix. And when this alarm goes to alarm state, you can actually take action to automatically recover the instance. So if there's a hardware failure, alarm is triggered, and if you had specified automatic recover, the instance is replaced. The failed instance is replaced with an instance that has the same type, same instance ID, same IP addresses, and in the same placement group. So it's almost as if the failure never happened. Now, when you launch an instance, there's a whole bunch of configuration you have to think about. And EC2 service helps you with every aspect of instance configuration. So in terms of what software runs on the instance, some packages are already baked in the AMI, but you can install others from external repositories or from AWS repositories. And note that it's important to periodically update your instances with latest security or performance patches. The OS users, each instance has a default user account. Depending on the instance type, the username is EC2-user or root or admin or CentOS, etc. But in addition, it's safe from a security perspective to add more user accounts on your EC2 instance with separate permissions and file spaces. Each instance has a clock, and if the time on the instance drifts away from the real time, this can cause problems in distributed protocols, or the AWS CLI SDK requests can also fail if this queue is too large. So to prevent that, AWS provides a time sync service that you can use to synchronize your instance clock. So there is an NTP, Network Time Protocol endpoint, at this link local address. You can use this to sync time. Now you can set the host name of your instance. By default, the host name of the instance is built from the private IP and the region. It looks like this. So IP.region.compute.internal. If the instance is assigned a public IP, it also has a public name that is built from the IP and region, and that looks like this: ip.region.compute.amazonaws.com. Now remember that this name can change each time instance stops and restarts. If you wish to maintain a constant name, you can use a dynamic DNS service. So you can have a fixed and friendly name, for example, Acme Proxy, but you need to update the dynamic DNS service each time the public IP changes. Another solution is to use an elastic IP, which you need to allocate and assign to the instance, and use a DNS service to map a fixed and friendly name to the elastic IP. Hostname on the instance can be changed to a public DNS name. The other configuration thing to consider when you launch an instance is to initialize the instance and do software installation, configuration, and so on. So EC2 allows you to run custom code to configure a brand new instance. But how do you specify this code? So one of the launch parameters is what is called a user data parameter. And it's part of the launch wizard, and it's also part of launch configuration or launch template. This is the parameter you can use to specify the commands that must run at launch. And this user data value can be a plain text, or it can be base 64 encoded text in case you have some non-ASCII characters in your script, or it can be a file. Note that this user data script runs only on the first boot and not on subsequent starts, but you can configure it to run on every restart. And also note that user data can be changed later, but to change it, you have to stop the instance first. There are two types of user data. You can have shell scripts in it. Note that these shell scripts are run as the root user, or you can have cloud init directives. Now, cloud init is a package provided by AWS, which contains high-level commands, and these commands make it really easy to configure instances. And you have a variety of directives for common configuration functionality, such as installing packages, updating packages, running shell scripts, mounting volumes, etc. Now, another aspect of instance configuration you have to think about is CPU options. So you have the ability to customize the number of cores. And why would you do that? In case your software licensing is on a per core basis, you can control that to control your licensing costs. You can also control the number of threads that are run per core. So once vCPU is one thread, you can change CPU options at launch time only. And changing CPU options does not change the cost of the instance type that you are launching. And finally, instance metadata is an important aspect of instance configuration. So what is instance metadata? It's data about the instance that is used by configuration scripts and that is set by AWS. This data is available on the instance at a link local HTTP endpoint. So these are some endpoints: 169.254, 169.254, latest metadata or latest user data. And this is the same user data we talked about earlier, which you can pass in to run scripts at launch. Now, let's look at some examples of the metadata. So what do you find under latest metadata? So you can have /latest/metadata/AMI-ID. You retrieve that, you get the AMI ID. Similarly, there's other attributes: instance ID, local hostname, public hostname, local IPv4 address, metrics of the instance, the public IPv4 address, public keys, security groups, and so on. As you can imagine, all of these can be used by scripts to manage the configuration of the instance. Now, access to instance metadata by default is available to any process running on the instance, but you can set up a local instance firewall to limit access to metadata to only certain users and groups. Now, instance monitoring. You have automated tools to monitor your instances, which is a key aspect of managing your workload, or you can use manual tools. The manual tools are the EC2 dashboard, where you can see all the details of all your instances. You have the CloudWatch dashboard, where you can graph instance metrics, and these graphs give you an indication of how your Fleet is doing. You also have a bunch of automated tools to monitor your instances. So AWS provides system status checks. Now, these are checking the status of the hardware, and any failure here is something that AWS can fix. However, as a customer, when you detect a system status check failure, you can stop and start your instance and or replace it. The instance status checks are issues that customer can fix. These are not hardware issues. These could be an instance running out of memory or running out of space. You can use EC2 metrics and alarms supported by CloudWatch. So there's basic monitoring that comes for free at 5-minute intervals, but you can opt for detailed monitoring, which gives metrics at 1-minute intervals. And you can set up alarms based on threshold values of different metrics to automatically stop, terminate, reboot, or recover instances. You can additionally install a CloudWatch agent. You can use that to collect logs from the instance, and also you get additional metrics. You can use CloudWatch events and CloudTrail to monitor and manage your instances. And AWS Systems Manager has a patch manager that you can use to keep instances and your applications patched with security and performance updates. Now, this is unusual and rare, but AWS has a notion of scheduled events. So whenever there is a need for AWS to reboot, retire, stop, start any instance, it sends an email in advance notifying you of that. And this is essentially a maintenance activity that is done from time to time. For example, if a certain hardware needs to be retired, AWS has to move all the instances off of that hardware. Now, CPU performance burst, certain instance types provide this feature. So most instance types are fixed performance instances, but some types are burstable performance. And what that means is that these instance types have a baseline level of performance, and that's a percentage of a core, and that percentage varies. Well, let's say it's 5% or 20% or whatever. Now, the burstable performance instances can actually burst above the baseline using what is called credits. So one credit gives you a full core for a minute. Now, once the credits are all used up, you incur extra charges when you burst, when your application usage spikes beyond the baseline level of performance. Now, these credits are automatically accumulating at some rate. For example, it could be 12 credits per hour or 5 credits per hour. When the usage is below the baseline level, these credits accrue. When the usage bursts above the baseline level, these credits are consumed. And when the credits run out, extra charges are added to your bill. These are useful if occasionally your workload usage spikes. Now, AWS provides a lot of flexibility in how you purchase compute capacity. So these are the different ways. With on-demand, there is no upfront payment. There is no commitment of any time period. You just pay for whatever time you use. And it's the most flexible purchasing option. This is good for, workloads that are very difficult to predict. They could be spiky at unpredictable times, and these workloads cannot be interrupted. Another case where it's useful is when you're developing a new application and testing it. Since you don't have a profile of the application yet, it's difficult to predict its usage. Then you have spot instance purchase. So with spot instance purchase, you're getting almost 90% off on-demand prices. So what you're doing here is you're saying, if there is spare capacity, I'll buy it at a price I'm willing to pay. So you specify an instance type and a price you're willing to pay. These spot instance prices, they fluctuate up and down based on the demand for compute capacity and the availability. If the price happens to fall below the price you're willing to pay, the instance is allocated to you, and the price charged is the spot price, by the way, and not the price threshold that you set. But when the price rises above the willing to pay price, or AWS decides that it needs the capacity, the instance is interrupted. There is a 2-minute notification, and then the instance is taken away. Now, when an instance is interrupted, you have the option of stopping it, hibernating it, or terminating it. If you don't specify an option, it is terminated by default. When interrupted, if you need the option to keep the instance for a minimum duration, you can specify that minimum duration, and that can go as long as 6 hours. But as you can imagine, that will reduce the discount you get on the EC2 instance. So when is spot instance purchase useful? This is for workloads that have flexible start and stop times and can be interrupted. For example, offline batch processing. It's also useful for cost-sensitive applications. A spot fleet is an extension of spot instances. Essentially, with a spot fleet, you can request and manage multiple different spot instances that are needed for your entire workload. Let's say you're running a Hadoop cluster. For that, you can use this. So for a spot fleet, you can say what target capacity you need in terms of number of instances, vCPUs, memory, storage, network throughput, and so on. And AWS takes care of maintaining that capacity. This fleet can span availability zones, but it cannot span regions. Savings plan is another purchase option where you're making a commitment. So this is the first purchase option we are discussing with a commitment. So you commit for 1 or 3 years in exchange for discounted prices. So for this 1 or 3 years, you commit a certain dollar amount. There are two types of savings plans. One is an EC2 Instance Savings Plan, and the other is a Compute Savings Plan. So in this EC2 Instance Plan, you are committing to using specific instance families in a specific region, and you get up to 72% discount. In the Compute Savings Plan, you have more flexibility in terms of deciding instance family, the instance type, availability zone, or even region. However, the discount is lower. You get up to 66% discount. But the advantage is you can also use it for Lambda usage and Fargate usage. So this is not restricted to EC2 instances. A reserved instance plan is where you are making a commitment, but you're committing to specific instance types and not committing a dollar amount. You get up to 75% off of on-demand prices, and in exchange, you're reserving capacity for 1 or 3 years. You have to choose a region that cannot be changed, unlike savings plans, which have a region flexibility. So there's two types of reservations. So standard reserved instances or convertible reserved instances. In the case of a standard reserved instance, you get a certain discount. The instance family is fixed, but you can change the availability zone or the instance size when you launch. And note that for very high volume purchases, you get an additional 10% discount. And when you have consolidated billing, all the sub-account purchases, they are added to the total volume for discount consideration. In the case of a convertible reserved instance, you get a smaller discount, which is 54 versus 75 for this, but you have a lot more flexibility. You can change the instance family, availability zone, instance size, operating system, tenancy, and so on. Now, for a reserved instance purchase, there are 3 payment options. You can pay the entire commitment amount upfront, which is so whatever instances you selected, the cost is calculated for the period you selected, and you pay it all upfront. The hourly price that is used for the computation of the amount has the highest discount. You can pay a partial amount upfront, where the discounted hourly pricing gets a medium discount, or you can have no upfront payment, where the discounted pricing used for the computation is lower. Now let's look at an example pricing for the A1 dot medium instance type. So here's the standard 1 year, standard 3 year, convertible 1 year, and a convertible 3 year. If you look at the discount, the highest is for a standard 3-year term. You get the highest discount. This is the savings over on demand. So this is the on demand hourly price, and this is the effective hourly price in this plan. As you can see, for a shorter term, it's higher, and for no upfront, it's the highest. When you pay all upfront, you get smallest price and the highest discount. And if you go from standard to convertible, you can see the discount drops because you have more flexibility. Now, when you buy a reserved instance, when you make a reserved instance purchase, you can scope the purchase to a specific availability zone, in which case it's called a zonal reserved instance, or a specific region, in which it's called a regional reserved instance. Now, when you scope an RI purchase to a zone, it actually becomes a capacity reservation, which means capacity in that availability zone is guaranteed to be available for your application. In the case of a regional scoping, there is no capacity reserved for your purchase, but you have the flexibility of using your RIs in any availability zone. And you're allowed to change the scope of an RI over time. Another advantage of RIs is that you can trade them on the AWS reserved instance marketplace. So in order to sell, you must have owned for at least 30 days, you must register as a seller, and 12% of the sale is charged as a fee by AWS from the seller. Now, when is a reserved instance purchase a good thing to do? When you have applications with predictable usage, for example, an e-commerce server that needs to run 24/7, or apps that require a guaranteed capacity. So once you know that, you can commit to a certain period and you get a discount for that. Now, capacity reservations is another way to purchase EC2 capacity. You can choose an availability zone and an instance type and a quantity and have AWS reserve that capacity for you. But once that reservation is active, whether you use it or not, the capacity is held for you and it's charged. You can change the reservation over time by changing the number of instances and when the reservation ends. You can also share a capacity reservation with other accounts. And note that by default, a capacity reservation is at on-demand pricing. And as we just saw, reserved instance purchase scoped to a specific zone is also a capacity reservation, but at a discount. But if you don't want to be tied to a commitment of a certain time period, you can go for capacity reservation at on-demand pricing, where you have the complete freedom to change the reservation and choose the end time. Now, if you happen to have a RI purchase, how does it affect capacity reservations? So as I said, you can purchase a capacity reservation without any RI and you don't get any discounts. But if you had a savings plan purchase or a regional RI purchase that is active for the availability zone and the instance type chosen by the capacity reservation, then there is a discount applied to your capacity reservation. And like I mentioned, a zonal RI, which is scoped to an AZ, is already a capacity reservation with a discount. So that zonal RI will not be applied to on-demand capacity reservations in that zone. You can also have scheduled reserved instances, which means you're reserving capacity only at specific times on a schedule for a period of 1 year. So what you specify is the instance type, the availability zone, start time, duration, and the period, whether it's daily, weekly, or monthly. The pricing of scheduled reserved instances can fluctuate, but at the time you create a schedule, whatever pricing is in effect is what applies. And the discount associated with scheduled reserved instances, because you're reserving capacity, you get 5% off on-demand prices for schedules that are at peak time as designated by AWS, and you get 10% off on-demand prices for off-peak times. Between savings plans and reserved instances, Amazon recommends savings plan because they offer similar savings but more flexibility. For example, you have free to choose regions for your instances with savings plans, but not with reserved instances. And you can also use savings plan commitment for Lambda and Fargate usage. Also keep in mind that any on-demand instance that you launch, if it matches a reserved instance purchase, it will get the RI discount. What's a dedicated host? So it's a physical host, but that's dedicated for a specific customer, and it has a certain amount of compute capacity. So a certain number of EC2 instances can be launched on that host. It supports a specific family, but you can have different instance types within that family. So a dedicated host is useful when you have your own software licenses to bring, such as the Oracle database license or the Windows Server license, and AWS helps with managing the license on the host. Or if you have a corporate compliance requirement that you must use a dedicated server, no other tenants, then a dedicated host is the right solution. A dedicated host has these different purchasing options. You can purchase it at on-demand prices, or you can reserve it for 1 or 3 years at 70% off, or you can get a savings plan with up to 72% off. When you launch instances with a tenancy of host, they are launched on your dedicated host. And the pricing is for the entire host, regardless of how many instances you run. You buy a host with a certain capacity and you pay for the entire capacity, whether you use it or not. And once all the instances that you've launched are terminated, you can release them. A dedicated instance, on the other hand, is just one specific instance, but it's running on hardware that is dedicated to a specific customer. So when you have a dedicated instance on a hardware dedicated to a customer, note that the same hardware could be shared between dedicated instances and non-dedicated instances for the same customer. Now, the tenancy of an EC2 instance is of three kinds. When the tenancy is default, the EC2 instance runs on hardware that's shared by many customers. When the tenancy value is dedicated, it runs on hardware dedicated to a customer. And when the tenancy is host, it runs on a host which is dedicated to a customer. An EC2 Fleet resource helps you manage multiple EC2 instances in one operation. And the instances could be of different types, in different availability zones, and across different purchase models. So it's a management construct, and it's a good feature of AWS EC2 service. It helps you speed up your workload setup, helps you optimize costs. Note that a fleet can span availability zones but not regions, and it can only be used via API or CLI and not via the EC2 console. VM import export is a feature that helps with migration from an on-premises to AWS. You can migrate your workloads, or you can also use it as a disaster recovery option. So if you have a disaster in your on-premise data center and you have exported your VM images to AWS, you can actually continue your processing on AWS using those VM images and running EC2 instances based on them. And when your on-premises is back in business, you can switch back to the on-premises. So it provides you a disaster recovery feature for your on-premises computing. Now, what are the different methods in VM import export? So you can import a VM from on-premise to an EC2 instance. You can import a VM image from an on-premise to an AMI. You can also import on-premises disks to EBS snapshots. And these EBS snapshots can become EBS volumes on an EC2 instance when you have a disaster in on-premises and you moved your computing to AWS. You can also export an EC2 VM so that when you restore back to your on-premise, you can use this in your on-premises data center. Now, as I discussed this earlier, Instance Connect is a feature which relieves you from the burden of managing key pairs in EC2, and it's a safer option that allows users to connect to EC2 instances with the extra capability that their accesses are audited in CloudTrail. Now, Nitro Hypervisor, it's AWS's own hypervisor. It's built on the Linux KVM technology, and it reduces virtualization overheads compared to the other hypervisor, which is Zen. But AWS does support instance types based on Nitro as well as Zen. Let's look at the quotas associated with EC2. The auto scaling limits are you can have 200 launch configurations per region and at most 200 auto scaling groups per region, and per auto scaling group you can have 50 scaling policies. Now, the number of PCI devices on a specific instance is 27 maximum for Nitro based instances, and each PCI device is equivalent to one EBS volume device or one elastic network interface. So if you add all your volumes and all your interfaces, it cannot exceed 27 for Nitro based instances. When you send email from your EC2 instance, it's important for AWS to maintain the reputation of its IP addresses. AWS wants to avoid its IP addresses being designated as an email spam source. So there is a limit imposed on the amount of email that is sent. And there is a limit on the number of on-demand instances. So the total vCPUs per region across all the on-demand instances is limited, and the limit varies with instance type. Now, what are the pricing aspects? One of the neat features of EC2 is that it supports per second billing of EC2 instance usage as well as EBS volume storage. The minimum build period is 60 seconds. The instance hour cost depends on the instance type, the OS, the bundled software, and the purchase model. Now, the EBS optimized instances have the capability that they have dedicated bandwidth between EBS and EC2 that is independent of other network traffic. Hourly cost for such instances already includes the charge for dedicated bandwidth. Now, data transfer costs. Any data, network data coming into EC2 is free of charge. When data goes out to the internet, there is a per GB charge. Data going out to CloudFront is free, but of course there is a charge from CloudFront out to the internet, and that is defined by CloudFront pricing. And if data goes from an EC2 instance out to other availability zones or regions, there is a per GB charge. There is a charge for elastic IPs. One elastic IP per instance is free. Additional elastic IPs are chargeable. Also note that if you allocate an elastic IP, but you do not attach it to an instance in running state, then there is a charge for the elastic IP. This is to discourage hoarding of elastic IPs, which are limited. Now, what the free tier provides is for a period of 12 months, you get 750 hours of T2 micro instance per month, and you can run Windows or Linux on the instance. Now, what are the various EC2 metrics that you can see in CloudWatch? There's CPU utilization, the network read-write data on packets and bytes, the instance store read-write ops and read-write bytes, and the EBS read-write ops and read-write bytes. So basically CPU network storage. You can get additional metrics, but that requires you to install the CloudWatch agent on the EC2 instance. In addition, you can get memory and disk space utilization metrics, and you can also collect logs from the EC2 instance using the agent. Note that you can view the metrics along various dimensions. You can view it by instance, by an AMI, by an auto scaling group, or for all the instances. In terms of integration with other services, as I mentioned, EC2 is sort of the brains of the AWS cloud, and it is integrated with many services. Some of the services even use EC2 behind the scenes. So the identity access management, you need to set up permission policies for EC2 usage and APIs. ELB routes traffic to EC2 instances and is integrated closely with auto scaling. VPC instances are bound in a VPC in subnets. CloudWatch and CloudTrail integrated with almost every AWS service. EBS is closely bound to EC2 because that is where it is used. Fargate, RDS, Lambda, etc. use EC2 behind the scenes. And ECS, the Elastic Container Service, you can have EC2 instances on top of which you can run containers, CloudFormation, Elastic Beanstalk, auto scaling, and so on. Let's see how EC2 facilitates the 5 pillars of the well-architected framework. So very quickly, how is operational excellence enabled by EC2? Well, auto scaling helps maintain a healthy, available fleet. The instance resizing feature provides the flexibility as demand changes or as new generations of hardware are introduced. You can have automated instance recovery. There are system status checks and instance status checks that give you a window into the health of the instance. You have a patch manager that helps keep instances up to date. EC2 Fleet feature helps you manage groups of instances easily. And the Instance Connect feature, it removes the problem of key pair management and provides better auditing. In terms of security, you can set up software firewalls with security groups, and there are safe and secure PKI-based login mechanisms as opposed to password-based mechanisms which can be compromised. And note that EC2 service is PCI DSS compliant. In terms of reliability, the auto scaling feature helps you maintain a healthy optimal fleet automatically, and the automated instance recovery also handles failures associated with the instance, thus contributing to greater reliability. Performance efficiency. There are a lot of high performance options for CPUs, memory, storage, and network. And placement groups feature helps you with optimal placement of instances. For optimizing costs, again, EC2 Auto Scaling. It helps in right sizing your EC2 instance fleet to the demand. You can match the resource consumption to demand. You have a variety of purchase models to help you save costs based on your needs and requirements. You have a variety of instance types, and you have the per second billing feature that is useful to cut costs. That's it for EC2. Thanks for watching. Hope it was useful to you.